The sun. The great pendulum in the sky. All timekeeping by man depends on it. It is the thing that gives us our day and night, our seasons, and our life here on Earth. It has been worshipped for its life-giving properties and continues to affect every aspect of our physical existence. Without the sun, we would not be here. For untold ages, man has depended upon the sun and other stars to interpret and convey the passage of time. At the core of every microchip, every robotic and automated creation beats the heart of a simple clock mechanism. This mechanism is called an oscillator. By definition, to oscillate means to swing back and forth with a steady, uninterrupted rhythm. Arguably, the most iconic and memorable physical oscillator would be the pendulum. A pendulum is a weight suspended in the air, often attached to a bar or wire. Its origins ancient and largely unknown, the earliest surviving record of its study was detailed by renowned Italian scientist and astronomer Galileo. Due to his failing eyesight, he was only able to describe his idea of a pendulum-based clock, which would eventually be developed by others after his passing. The pendulum is wound up, creating a potential state of energy that is released and allowed to swing freely to the opposite side. Due to the effect of gravity, the pendulum is slowed to a halt and repeats this motion back toward the other side, forming a mirror image of itself, dividing a whole state of static equilibrium into two equal halves of motion. Each end of the pendulum swing serves as a physical representation of the idea of a moment in time. Each pendulum oscillation, we can create reference points to events and periods in succession, leaving impressions on our brains like vinyl records and solid-state memory devices to quote-unquote remember these changes. This creates our perception of the illusion of time, allowing us to recall certain changes we experience and plan for subsequent changes in what we call the future. This is the idea of keeping time, and without oscillations would not be possible. Forms of pendulums can be found in classic grandfather clocks and are also used in modern sensors and measuring components such as accelerometers. This same oscillating principle has been created electronically and can be found in nearly every microchip on Earth. The oscillations taking the form of electronic waves are measured in hertz. 1 hertz is equal to 1 oscillation per second. Oscillators and microchips create a small flow of alternating current from a flow of direct current, just like the pendulum swinging from side to side. These oscillations create the mirrored repeating patterns of moving current within a given time period, effectively creating a clock which is used to compare voltages traveling inside and out of a chip, schedule events and conditions which are executed with precision to accomplish a task, to put a chip to sleep for a period of time, etc., etc. These oscillators are responsible for your phone operating properly, so you can watch millions of pixels turn on and off faster than you can perceive in order to watch this video and allow the sound to be pumped through the coils of wire in your speaker to push the magnet attached to the diaphragm that creates the ripples of sound through the air to your ear. These oscillators run your airports, your train stations, delivery logistics systems, and favorite website servers. In effect, these oscillators run your world. Why not learn how to use them? From the moment you apply power to a microcontroller, the oscillator begins to run. Chips are configurable to run at different frequencies. This is often done by setting certain fuse bits when flashing code to the chip, but can also be set in the code of any program written on more modern chipsets. The oscillator on board allows the chip to count in increments and to go through and execute each step of the code written to it. The oscillator is what also gives the chip the ability to execute code in an unending repeating loop, just like a daily repeating routine one carries out according to the swings of a pendulum clock. Every peripheral on the chip is dependent upon the precise timing and consistency of these oscillators, and one of the most useful and fundamental peripheral is the timer counter. We can use the timer counter along with the interrupt peripheral, which will act as a trigger that activates under the specific conditions we write for it. Let's use our Atmega 328PU chip, along with the AVRC language. Even if you are used to Arduino or Python languages, the C language will help you to understand the logic in our clock concept more clearly. The timer counter peripheral has its own oscillating clock mechanism separate from the chip's oscillating clock. We will tap into it to create our countdown timer using minutes and seconds, and then triggering a pin connected to an LED when both of these reach 0. We will include our basic input-output and interrupt header files in our preamble. Next, we create a volatile variable for the ticks of the oscillator, followed by variables for our minutes and seconds. Volatile variables mean that they can be used anywhere in our code and the values changed. It will take a lot of ticks to equal 1 second, so our oscillator ticks will be a 16-bit number. Our minutes and seconds only need to be 8-bit numbers. We can set them to any number we want. Let's set our countdown to start at 1 minute and 60 seconds. Now let's set up the actual timer counter. We don't need anything fancy, just the 8-bit timer 0 that is on our chip. We will set it to normal mode, and since we will set our fuse bits to make the chip run at the maximum 8 MHz, the oscillator will need 31,250 overflows to equal 1 second. That's extremely fast, isn't it? Next, we will tell the timer counter peripheral to enable an interrupt trigger with our overflow option. After that, we set up the interrupt that will trigger for our overflow condition. You can look this up in the datasheet and it will seem very confusing at first, but it's merely a bunch of options, and this is what we need. An interrupt service routine that deals with timer 0's overflows. Each time it is triggered, we are going to increase the ticks of our clock by 1. That's what the plus plus means. It takes the existing ticks value and increases it by 1. If you were to count down, you would use minus minus. For now, we will count up our ticks of our clock each time our oscillator overflows 31,250 times, which is equal to 1 second if our chip is running at 8 MHz. If I can understand it, so can you. Write it down a few times. You got this. Just be patient with yourself. Now, we need to make a skeleton for our actual clock concept. I am going to show you a cascading effect that is going to blow your mind. We are going to make a digital version of a mechanical gear clock. We start by creating a function we will call countdown seconds that doesn't need to take into account any outside parameters. It's just going to do what we want it to inside the function. That is why we write void in the parentheses. We made a value of 60 for our seconds in our preamble. We made it volatile so this function can make changes that will be remembered. We will decrease by 1 second here. Then we use an if statement to trigger the minutes countdown variable when our seconds reach 0. We also reset the seconds back to 60, immediately ready to be counted down again. While resetting back to 60 seconds, we'll tell it to trigger the countdown minutes function, which we will lay out in just a second. This is the cascading effect I was telling you about, working just like the gears inside of a clock. Once we close the door to that if statement, we will toggle an LED connected to pin PB1. So every second the LED will alternate between on and off. We have completed our countdown for our seconds. Now we set up our minutes countdown that triggered when the seconds reach 0. Let's give this function a similar name to the other, countdown minutes. We will also subtract 1 minute each time it is triggered. We will also have an LED attached to pin PB2 to alternate on and off each minute that goes by. Notice most of our code has been outlined in our preamble. In our main area, we simply set the pins on port B to output electricity. We call our timer 0 to the stage and we enable global interrupts with this code right here. Everything is ready to go. In our loop, we need to set an if statement. If our ticks count up to equal 1 minute's worth of ticks, then we reset it back to 0. Then we trigger our countdown seconds function, which will then trigger the minutes countdown function. You'll notice that my ticks have changed to 31,800. In theory, 31,250 is correct for the 8 MHz speed. However, after looking at how it was actually functioning on the chip, I had to make this adjustment. Now for the final piece of code. So we have our timer working, it's counting down minutes, it's counting down seconds. When the countdown reaches 0 for both, we want it to trigger the pin PB4. I did this by creating a separate function just to make the code a little bit clearer, although you don't have to necessarily do this. I labeled this function boom. All boom does is it tells port B to turn on pin PB4. In order to call boom into play during the loop, we will set up a nested if statement. This is simply an if statement within another if statement. We set it up like this. If minutes is exactly equal to 0, and if seconds is less than or equal to 1, then we trigger our boom function. I had trouble getting it to work with the seconds equaling 0 because the seconds resets to 60 and I haven't used any delays in my code. The reason I didn't use delays is because it stops the chip completely for that amount of time, and I didn't want it to get into the way of my accuracy for my timer. All right, let's see this thing in action. Oh, I just remembered. There's something about the boom function that I need to tell you.